Assalamualaikum warahmatullahi wabarakatuh. Hi everyone, my name is Kunti Inayati. I'm from Universitas Muhammadiyah Gresik. In this short video, I like to share my research paper. It's about MongoDB and indexing. So the main question is, when you have like 30 million records, which indexing strategy is the fastest and how much storage does it use? So in this abstract, it's basically the summary of the whole paper. I tested 3 indexing setups, used 13 million e-commerce records, and found that compound index is the best option, especially for queries with multiple filter conditions. So the introduction explains why this topic is important. Imagine you have an e-commerce app with millions of transactions. When someone searches for something, the database needs to find it fast. Without indexing, MongoDB has to check every single record one by one. And that's really slow when you have a lot of data. So, that's the problem this study tries to solve. For the data, I use a synthetic e-commerce dataset from Kaggle. It has around 13 million order records. Each record has fields like product ID, order status, price, and quantity. But in this paper, I just used the large collection, which is the order lines. So here's how I did the experiment. I tested 3 conditions: no index, single index on product ID, compound index on product ID and status. And I tested each one on 4 different data sizes, from 1 million, 5 million, 10 million, and 13 million records. So I can see how each strategy performs as the data gets bigger. Then I used, okay, this is the research workflow, yeah, you can see on the screen. And then I used 2 queries. Query 1 searches by product ID only. Query 2 searches by product ID and order status together. Each query ran 30 times to get a stable average. What I found was the index type. What I measured was query speed, build time, and storage size. For the environment, I run everything locally on my own laptop on a i5 processor, 16 gigabyte of RAM, SSD, and the MongoDB version is 8.2.6 with Python. Yeah, okay. Now let's jump into the result. Here are the results, and this is the detailed query execution performance metrics. By this table, we know that without any index, MongoDB scans every document one by one. So as the data grows, the time also keeps growing. You can see it clearly in this graph. At 13 million records, it's become really slow. But then when added an index, both single and compound, the execution time dropped to just a few milliseconds. That's a really big difference, isn't it? And then for the single field query, single index is slightly faster. That makes sense because it's Okay, that makes sense because it's made for that one field only. But for two field queries, compound index is about 6.8 times faster than single index. Because compound index already covers both fields, so MongoDB doesn't need to do extra work. Now for storage. The difference between single index and compound index is only 1 megabyte at 13 million records. So even though compound index covers two fields, it doesn't cost much more storage because that's because the status field only has 5 possible values. So it's very efficient to store. And then you're going to the trade-off. So this is the main point. Compound index is much faster for multi-field queries and only costs 1 megabyte more storage. So the trade-off is really worth it. And I also checked the query plan for MongoDB. Every time I added an index, MongoDB automatically switched from collection scan into index scan, so the optimizer worked correctly in all conditions. Okay, the last one is the conclusion. The conclusion is if you have large data and your query use multiple filter fields, compound index is the best choice. It's fast, it scales well, and the extra storage cost is very small. For future work, it would be interesting to test this on a cluster setup and also measure RAD performance. Okay, that's my paper. I think that's all. Thanks for watching. Wassalamualaikum warahmatullahi wabarakatuh.